So here we have move all zeros to the end. Okay, let's read the question statement. Well, the problem says given an array of integers ARR, the task is to move all the zeros to the end of the array. Okay, while maintaining the relative order of all non-zero elements. Fine. And one more point is mentioned here that changes should be done in place. What does in place mean? In place means that the array that we are given, we should only make the changes to that. We shouldn't use any extra memory. So now let's try to see the sample test cases for a better understanding. So here, as you can see, in this sample test case, we have 1, 2, 0, 4, 3, 0, 5 zeros. One zero is here, another one is here, and one is at the last. What do we have to do? The task is to move all these zeros to the end of the array. In the output array, you can see we have moved all the zeros towards the end. The relative order of the non-zero elements is still maintained. Okay, so it is 1, 2, 4, 3, 5. 1, 2, 4, 3, 5. Okay, we have not changed the sequence of the non-zero elements at all. Okay, and I have one more sample test case here. Well, in this case, you can see no zeros are mentioned. That means we don't have to make any change. As it is, the array that we have to keep it like that. Okay. One scenario could be that all the elements are zero. In that case, to what can you move? That array is not going to be having any change. Fine. Okay, let's try to develop a logic around it. Although it is being asked that we have to do this question in place, but if we have to make use of some temporary array, won't it be much easier to solve this question, right? So let's see this approach first. So what do I have to do here is I will take under the consideration of this array, and what I'll do is I will fill this temporary array, but only with the elements which are non-zero. So I'll traverse through ARR. Let's suppose my I is here, beginning from here. I would keep my 1 at the 0th position, this one, 2 at this one. Now I have 0. Once I reach 0, I don't need to put it in my temporary array. I'll move ahead. Now I got 4. I will put that here in my temporary array. Then I'll put 3. 0 is going to be skipped. Then 5, I'll put 5 here. Okay. And then again 0, 0 is skipped. So once the traversal is done of this array ARR, then I would be left with this temporary array filled so far. Still the positions are left. Well, all these positions you can explicitly fill these positions with zeros because these are only going to be left spaces for zeros. Okay, we skipped 3 zeros, 3 spaces are left. Make sure you are taking temporary array of the same size of your ARR. Okay, so this approach is quite simple. Okay, you can do this on your own, but the thing is the question does ask that we have to do this question in place. We don't have to use any extra space. We have to make the changes within the array. Okay, so for that, how can we approach this? So seeing this approach, when we are using some extra space, what is going to be the time and the space complexity? Okay, well, time is going to be order of order of n, because we are performing only one traversal, right? Talking about the space, well, it is going to be order of n because we are using one explicit extra array for our solution, correct? The question does not ask that, we have to remove it. Now for removing, what could be a better approach in your mind? Let's try to see this. What if I make some changes to my pointers? Okay, here I am keeping this pointer, and this would be keeping the track of the position where 0 is held. Okay, and I would replace it with the next value. Okay, let's try to understand it in this way. I have my I variable, or you can say I pointer, and I have to perform a little something wherever I get a non-zero element. Okay, so here, let's say I have 1, I've got a non-zero element, right? So I would perform something. You need not to look here right now. I move to this point. I will perform one operation. Then I move to 0. I will simply skip and I would go further. Okay. This is how my I is going to be driven. Now let's see what function or what is the thing that we are doing here. Whenever my I is having a non-zero element, I would keep that element at ARR count. Okay, and how does count work? Well, count only and only moves when we have a non-zero element. Okay, let's see it using a dry run. Initially, my count is kept at 0 and so is my I. Fine. Now, once I have got a non-zero element, what will I do? I'll keep this ith element at the count. That means here it is going to be no change because both are pointing at the same position, right? Once it is done, this statement is done. What I'll do, I'll increase my counter. My counter is increased. For the next iteration, I is also increased, right? Nothing will happen so far because both are pointing at the same thing. Now my counter will increase and my I will also increase. Now here is the actual part. This time no swapping will happen. And whenever, sorry, I said swapping, but no movement will happen of this kind. But what will happen is that my count, this count is not going to move. It is going to stay here, holding the position where the element should be, a non-zero element should be, right? My I will move for the next iteration, but my count will stay here. The moment I get a non-zero element, such as here, what I'll do, I'll perform this. I will keep it at ARR count. So here, this 0 would be cut with, would be replaced with the value which is at I. In our condition, this 4, right? And once this happens, my count moves. So my count will come here. For the next iteration, my I will move to the next element. On this situation too, you can see I has a non-zero element. So whenever I has any non-zero element, what will happen? I will keep that element at the count's position. So here I'll have 3, right? Again, whenever I am replacing elements, I'm moving my count, and I is moving in every step because that is driving my recursion. That is driving my iteration. Now at ith we have 0, but in this case count will not move and no this shifting is going to happen. My I will continue its movement. Now at this point I encounters a non-zero element yet again. So when this happens, I know where do I have to keep it, at the position of count. So this will be kept here. All right. And then after this, I would move one step more. I would get the 0, right? Doesn't we don't have to do anything. I will go past the array. That means the iteration is done. That's all. Now you can see your count is here at this position at your last non-zeroth element. Well, beyond this, what you have to do is you again have to run a loop so that you can place all the values as zeros, because you would have such as this 5, you can have more values which are still non-zeros, which actually should be 0 once we are moving all the zeros at the end. Okay, this is how you're going to approach it. Now focus a little. How many iterations are we performing here? In the worst case scenario, how many iterations would be required here? Well, for the usual cases, you might have to only travel halfway through or so. But for the worst case, let's say you have all the arrays to be 0, all the elements of the arrays to be 0. Then for the first iteration, because I do have to check for non-zero elements, I would go from this point till this point, correct? And because you would not encounter any non-zero element, your count would still be here. So in the next iteration, your count will begin from here and will end till here, making all the values 0, correct? So now in this scenario, the worst case, you can say you are using 2 iterations here. Okay, you're using 2 iterations here. Also, if we talk about the complexity of it, we are having 2 iterations. That means we are going to be having order of 2n, right? Order of 2n time complexity, which can simply be said as order of n, right? Now, talking about the space complexity. Well, the space complexity is going to be constant. That means order of 1. Why? Because we are using no extra space here. All right. So let's also see, this approach is kind of very optimal. We can optimize it a little further, but this approach in itself is very good as well. Let's see how it is going to be implemented in code. Okay. So seeing the code of it, I've placed my counter as told, and now I am moving my I from 0th position till the end of the array. All right. Every time I encounter a non-zero value, I will keep the ARR I, that means the ith value that I have at count, at ARR count. Simple. and I would increase my counter only when I'm performing this statement. Fine. By the end, my count would be placed at a point where, from where after all the elements should be 0. That is what I'll do here. I'll take my counter, I'll move till the end of the array, and I'll make all the elements so like in the path as 0. Simple. So we've already discussed the complexity of it. The time complexity is going to be order of n. The space complexity is going to be order of 1, right? Moving ahead with how we can make it a little better solution, okay, in which we do not have to iterate twice, okay. For that, we would be using the same approach, but I'm going to tweak it a little. Instead of keeping just the track of the next element and making the count go making the count go one step ahead and copying the value, I would swap them instead. So in this approach, what we will do is we will going to be using the previous one only, but with a slightly tweaked method. Okay, instead of moving the elements and trying to copy the elements from the ith position to count, I would instead swap them so that the 0 that we have here also goes to the end of the array. Okay, let's try to see that here. Assuming my count is kept at the 0 initially and my iterations is starting from here. Again, I have to only perform the operation when I encounter a non-zero value. Okay, so I have my count, I have my I. I saw at ith position I have a non-zero value. What will I do? I'd simply swap the ith and the count value. Okay, both are same, nothing is going to happen. For this one, again, count would be increased, it would be here, and the value I would be here. Again, because both are at the same position, no swapping will happen. It will happen, but it won't affect anything, right? Then and I go here at this point. Now you can see your ith position is having 0. What will you do? Well, you are not going to increase your counter. You are not going to perform any swapping. You would just move ahead. You would just move ahead. That's all. Now you have encountered, you have seen this value. Okay, at this point you saw again a non-zero value. So once a non-zero value is there, what do? Well, you perform the swap. With which element are you going to swap it? With this 0th element. Now moving ahead, what will you do? You'll go here, right? You have encountered, and also the count will increase. The count is increasing. The count has come here. At this point, you have a non-zero element again, and you have your count here. You will again perform the swap, right? And then your counter will increase. Now, once you reach till this 5, you again have to do the same thing once more. That you will slash this 0, like swap these two values, 5 will come here, all right, and these zeros will be here. So eventually the array that you would have is going to be 1 2 4 3 5 0, which was the needed array. Okay, let me just clearly write it once more. This would become 4, this would become 3, and this would become 5 with the swaps, right? So I hope this approach was clear to you. Let's try to see how it is going to be implemented in the code. So the code is written here. What are we doing? I'm placing my count at the 0th position initially, and my I is going to drive my iteration. Here, at every time, if I'm encountering a non-zero value, I would swap the two values, right? I would swap the two values, and I would increase the counter for the next iteration. Okay, so this is how I'm approaching this question. Now, how optimized has it become from the previous one? The previous one, we were performing two two iterations in the worst case, but in this one, even in the worst case, we are only going to perform one single iteration. Okay, so for that, time complexity would be order of n. Talking about the space, we are not using any extra space. It is going to be order of 1. All right, so let's try to simply run the solution and see how it is passing all test cases. Okay, so the code is mentioned here. I'm going to just compile it, check if it does not have any error. All right, it is giving us the expected output. All right, we have gotten the expected output. Let's try to submit that. So it has passed all the test cases successfully. So I hope you've gotten this approach, right? It does have a little trick that we are doing in the third approach, but it is simple if you're just going to dry run it yourself once. Okay, so give it a try. and pass all test cases. Thanks.